Hey guys, in this video I will share with you 6 things that pivoted my way of thinking about programming. Let's get started. The first thing that I would like to talk about is LeetCode. You know what it is, so I'm not going to explain. Instead, I would like to share my experience and what LeetCode gave to me. Well, since I participated in contests, I tried to achieve the best performance in both, in my algorithms and how fast I solve problems. Well, my result was not really high. I think the highest rank was about top 13. Nonetheless, I practice quite a lot every day, and I was able to obtain a very cool ability to program fast. Meaning, once I opened a problem, I was almost immediately recognized some patterns that I need to apply here and certain algorithms that I have remembered in my heart. So I immediately began typing. And well, maybe it's not really useful, this approach, in everyday commercial programming, but it gives you a way, like a sense of what you need to do in order to solve the problem. And of course, it increases the overall cadence, how fast you program and write code. So I think it's really important. And since your algorithms should be effective from the performance perspective and sometimes from the resources consumption perspective, I read quite a lot about internals of the programming language that I used back then. It was Python, so I elaborated quite a bit about collections and other important modules and components that I used frequently. So for me, it was like a platform for learning Python as well. And also, after maybe 1-2 months of participation and actively practicing LeetCode, I began writing explanation articles, and I think it's also useful and can help you understand the problem you solve better and to help other people with sharing a detailed explanation. Well, at least that I would try to do. So let's move on. During my career, I used several languages. I began with C#, a little bit Java, then switched to C++ and Python. Currently, I use Rust on a daily basis, and during this time I always tend to dig deeper into the language details, into standard library implementations, especially in collections, sometimes in the runtime and in the compiler. C# is quite an interesting language. It's compiled to the intermediate representation that is after being executed on the CLR. CLR is a common language runtime. It allows .NET ecosystem have several languages like Visual Basic or C# or F# that are compiled to the same intermediate representation, and then they can be executed on the same CLR as a virtual machine and runtime environment. As a result of my research about CLR, I even prepared a small talk and gave it into the local .NET community about an opportunity to hook executions on the CLR, which was quite interesting to do, and of course I obtained some experience with public talks. Since I used Python initially on LeetCode, I had to read quite a bit about collections and other frequently used modules, and it gave me quite a good sense of how Python organized internally, about its powers and weaknesses, and also read about CPython and implementations of Python interpreter. Speaking about Solidity, the disclaimer is I'm not a Solidity developer, but I am working in the blockchain domain, okay? From the very beginning, I made up a mental model of blockchain as a domain, meaning the distributed systems consensus and how popular blockchains are organized. And I decided to contribute to Ethereum ecosystem. Well, I have never wanted to be a smart contracts developer. For a reason I didn't have much interest in it, so I decided to contribute to the Solidity as a language. I always wanted to develop compilers, be in this domain, but other big and old languages with their huge compilers are really paramount mountains that is really difficult to approach. But Solidity was quite new, the compiler was quite small and easy to understand, relatively easy to understand, of course. Luckily, a couple of my PRs was merged into the compiler, and after that, during my daily work, I implemented several tools that conduct static code analysis for Solidity, and they're quite successful as users give feedback to me. With knowledge about low-level details of programming languages implementation that I use usually give me an opportunity to think about the code I write in a more rational way, meaning I don't really know on what machine with what resources available my program will be executed, so I try to not waste resources and be as much conservative from the resources allocation and time consumption perspective, and I think it's really important, especially in such systems as blockchains are, because we're quite limited. We don't want to allocate too much memory, we want to be fast, and we want to finalize the consensus as soon as possible. One concept that helped me a lot to make up a structural mental model about programs is a finite state machine, or FSM. FSM is actually quite a simple concept. You can think about it as a graph, and this graph consists of nodes and edges as usual. Nodes hold states of a program, and edges hold transition functions from one state to another state. Since edges are functions that describes transition rules in the graph, they react on the input and decide what the next state your program should switch to. As a simplified example, we can consider a light switch on the wall. The initial position or initial state of the switch, let's say, is being turned off. And once a user clicks on the switch, he changes the state of this machine from the state being turned off to the state being turned on. And because you change the state of the machine, something happens. Well, the bulb becomes beaming light. In software systems, finite state machines are used everywhere. If you think about a login system on a website, in a simplified way, we can describe it as a finite state machine as well. The initial state is user is not logged in and no input is provided. And then we can consider it as a fork with two possible states. In case a valid pair of a login and password is provided, we can authorize user to access, authenticate him, and switch our system to the state that indicates that authentication was successful. Otherwise, we switch our system to the either state of a failure authentication and then switch back to the initial state, or we can make up any suitable user journey in this case. And if you keep in mind this way of organizing processes and states of your programs, it allows you, and well, it allows me at least, to reduce the number of code you write, because you know the particular procedures that you need to implement in order to achieve a certain behavior that can be encoded by a finite state machine. It's very useful, it's very helpful, and I highly recommend you to become acquainted with this concept. Speaking about compilers and compilers development, FSMs are everywhere there. If you parse a language, you always use finite state machines because you need to recognize patterns. Imagine that you have a machine with the states and graph, and you're constantly traveling through, and once you find a particular subgraph, it means that you recognized and find a particular grammar construction that you can then process, and so on. So it's a very useful concept. Speaking about blockchains and smart contracts are actually by default a finite state machine. They change the state of the blockchain as a system according to the user input happening during the block time in transactions. And they have a special term, they're called as replicatable state machine, because this state machine, like smart contracts, the state machine is being replicated within all nodes in the blockchain. So this concept is really important here too, and really helps to think properly about the system that you use, implement, or want to design. Being familiar with several programming paradigms can give you a very cool ability to be able to think about problems you're approaching from different angles. My relatively small experience of using functional programming languages give me a lot, actually. Well, the first concept that we know is a recursion, right? In usual programming languages, recursion is allowed without any restrictions. So if a function calls itself inside its body, it's a recursion. The common problem here that can occur is stack overflow. It happens when a function calls itself and allocates more stack frames unless the stack is overflowed. With functional languages, well, at least those that I used, it's not like that. They demand you to have an accumulator that you must decrease all the time where a recursion occurs. It is called a structural recursion. So you need something that you track within the program, or you can syntactically actually track it to ensure that your recursion will not collapse your program and will not cause a stack overflow problem. A small tip here. If your recursive call is the last operation in the function body, then possibly a compiler is able to perform what is called a tail call optimization. This optimization unwinds the recursive call and eliminates the need to allocate stack frames all the time. So it's quite useful. Also, experience of usage functional programming languages give me a good insight about type systems, because functional programming languages usually have quite a rich type system. In imperative programming, I usually didn't think much about types I use. Just embedded types like integers or float point number types and collections, and then I design classes and so on, following OP patterns. You know what I mean. But in functional programming, it's not quite like that, and that's why. Computer science classifies these types in programs into different categories. The first category is scalar types, atomic types that cannot be split and considered by parts, the whole undivisible fragments, like integers, floating point numbers, or chars in C, C++. The second category of types are sequences. Sequences hold a number of scalars as an array or a vector or a list. It's like a single space or fragment of memory that is allocated for the sequence that can be addressed by an element. So we can address particular element in the sequence and we can iterate through. And also we can address the whole sequence, usually as the first element of which, so we can pass them between functions, you know what I mean. The third category of types is called algebraic data types. It consists of two subcategories, sum types and product types. Sum types are those that can hold one of the possible options. For instance, in Rust, there is enum, which is called option, that can hold two possible states or two possible arms, if we're talking in the context of enums. One is sum, something is there, and none. So it means this sum type can be either none or sum. Product types allows to combine several values together. For example, if you need to describe a point on the two-dimensional space, you need to have two coordinates to describe its location x and y. And to conveniently store these values together, you can make up a pointer z, sum type that will hold both coordinates. Now you will know how to scientifically name such things. Algebraic data types allows you to design type systems that can prevent you from making errors in code. For instance, if we consider an option, an example of a sum type in Rust, we can think of it as like that. Since there are two only possible ways to construct an option type, as sum or none, whenever in code we met it, we know that it can be in a state after the construction with either sum or none. It's impossible for an option type to be undefined or null or whatever analogy from other programming languages we can think about. Of course, I'm not saying about unsafe Rusts, passing row pointers or something like that. With that fact, we can, whenever we find this and handle an option, we can check both possible arms that this option was constructed from. Pattern matching is a complementary feature to some data types. Since we know that a sum data type can be constructed only with a certain number of constructors, when we handle an instance of some type, we pattern match it with all possible constructors it can be constructed with. It means that we for sure implement explicitly how we handle particularly constructed sum type, and pattern matching must be exhaustive, or it's a good practice for it to be exhaustive, in order to cover all possible arms or constructors. Knowing all this allows me to design data types that can help me during development. So I would rather fight with compiler errors than release code that will fail and cause some problems or errors during the execution. So it's a very good thing that helps me. Now let's talk about proof assistance, one of my most favorite topics. We, by the way, use proof assistance in Ferrara, in inference programming language, as a target for the compilation. So we use it to prove properties of code. So let's talk a little bit about what it means. Automatic theorem provers were developed to help mathematicians and other scientists to be able to effectively, in a reasonable time frame and resources allocated for it, assess mathematical proofs. Like if we assume that a theorem exists and a researcher thinks that he finds a solution, then he prepares a paper, scientific paper, and publish it to the scientific magazine. Before publishing actually and let the global community know about the result, the proof must be checked that it doesn't have any errors and it's ready to be published. As long as the proof size is relatively succinct, we can do it, or people can do it relatively easy, I believe. But what if a proof is large, like 10, 20, 50, 100 pages or more? Then it's, I think, almost impossible, because it requires so many work of so many people being involved in, so it's practically very difficult to arrange. So automatic theorem provers allows to implement the proof in a formal language, and then the prover itself can immediately assess it and check if the proof is organized properly and it really works. So you can rely on the prover instead of checking everything manually. Let's consider a very small example what a proof looks like, and I hope it can give you some sense of what theorem provers are. Let's consider a two example I prepared in Rock Proof Assistant to illustrate how it works. Here we can see a theorem about a addition commutative for natural numbers. It says that for all n and m, which are type of a natural number, the addition operation is commutative, meaning we can swap operands and the result will be the same. To prove this, we open a proof block, and on the right hand side we see a proof panel that highlights and us open-end goals that we need to prove in order to complete our proof. So we introduce our and m into the context, and then we use an induction. Induction is actually a mathematical operation or a mathematical approach that says that if we prove something for a certain case, we can then generalize our reasoning and consider all other possible cases. For our natural numbers, it means that we say that, okay, n is a natural number, any arbitrary natural number. We are doing induction over n. Our n in the first case is considered as being 0, so our case is 0 plus m equals m plus 0. And the second case is s n prime plus m equals m plus s n prime. Without explaining in details what this notation means, we can think about s as a +1 operation, and n prime is any other value of n except 0. So we can read it as if we add 1 to any other n value which is not 0, so this statement still holds. Then we need to prove both these goals. By simplifying, we can omit some already known and by proof assistant recognizable patterns, let's say, like 0 plus m. It knows that if you add something to 0, the result will be the same, so it can omit it automatically. So we need to prove that m plus 0 is the same as m. And since we have a standard library with already proven theorems, like in our case, plus n0 theorem, we can apply it by rewriting the part we are interested in the following sense. We see in the tooltip that for all n of natural number, n equals n plus 0. In our case, we have n plus 0, so we can rewrite it in the backwards, meaning we can replace n plus 0, in our case it's m plus 0, with n, in our case with m. And this is what happened. Like we would not drop the 0 plus 0, but we just rewrite our part we considered with the theorem, with the initial premise. And then reflexivity means that both parts on the both sides of around the equal sign are mutually equals, meaning we can swap them and the result will be still the same, still holds. Now the second goal we need to prove is that we can add 1 to any other n except 0, and our statement still holds. We simplify our expression as usually. In this case, we move this plus 1 out from brackets, and we can use, as you see in our goals, here we have available assumption that we stated in the induction section. So we can rewrite either left or right side as we want. And here we are applying it and swapping parameters m and n, because we see that this is our inductive assumption that we can do it. Okay, and now we have this statement, and as you can see, the left and right sides are different. So we need either move this s from this right expression, or if we haven't died the rewritten of we had to swap the operation. In our case, we have already proven theorem that we can use to rewrite the right hand side and move s out from the brackets, and it will look like that. And now we see that both parts are equals, and we can apply reflexivity to close the last goal, and QED means that our proof is completed and we are done. So Proof Assistant does all work for us, so we can read it and understand what the proof is, but it's not necessary to do. Proof Assistant can do it after us. Of course, the example we have considered is small, but even with a little bit time spent with Proof Assistant can be beneficial, I think. For me, it works like that. After spending couple months with Proof Assistant, I noticed that I became thinking about the code and programming in a more general way. I mean, when I design a function or implement a function, I always think like, okay, the parameter actually can be any value, can hold any value. Like if it's an integer, it can be any. Of course, it might be obvious, like of course everyone knows, but when you feel it inside and when you think about it in a way like, oh, of course it can be, but do you really consider every possible value of an integer or any other type you can do? For me, it was not like that, but after becoming familiar with Proof Assistant, it became a case. Okay, this video was quite long, and even my accent light lamp ran out of charge, so I have to plug it into the socket, so hopefully the frame is still good. The final point in my narration is reading papers. I cannot overestimate how important it is actually. I can spend like 1-2 weeks, 2 hours a day for only one paper, but the outcome is amazing. I read papers slowly. I highlight important things, and if something is not clear to me, I'm not skipping it unless I clearly understand the concept completely. I ask ChatGPT to explain me or to refer to other papers or readings from where I can get more context about the problem, and this is how I approach it. Here, it's not that important how many papers I think you read. More importantly is to doing it and not stopping. The only one a month is good enough, I think. By the way, I have an idea in my mind and I would like to hear your opinion, so please leave a comment if you're interested. Since I'm constantly reading papers, I am thinking about recording a video with showing how I do it and, reading aloud, thinking aloud, so you can see my approach, or alternatively, we can make up a live stream and read interesting papers together. So please let me know. Okay guys, that's it. There were 6 things that pivoted my way of thinking about programming. I hope you found them interesting and you will repeat after me some of these steps and they will be helpful in your career and in your daily work. Thanks for watching. Please follow us on GitHub and leave comments, your thoughts, and we're appreciative for stars on GitHub, by the way. So cheers.